Okay, so today we will talk about linear regression with multiple regressors. Given that we already know one regressor. Okay, so we'll start from omitted variable bias. We'll introduce some new concepts as why we need a multiple regressor instead of just one single regressor. Okay. And then I'm going to talk about using regression to estimate causal effects, multiple regression in OLS. And then we'll mention more about measures of fit. Okay. At the last two parts, we're going to talk about sampling distribution of the OLS estimator with multiple regressors and control variables. So at the end, there will be some mathematics, okay? Those things will not be required, okay? So I'll mention that once we get there. Okay, so what is omitted variable bias? Let's get back into our example first. So in our class size example, beta 1 is the causal effect that we're interested in knowing, okay? That is how much would the score change given that, or how much would the score change if we change 1 unit of the student-teacher ratio, okay? And we want to know the causal effect. So if we want to know the causal effect, then those 3 assumptions have to hold, okay? And one of the most important assumption is this conditional mean equal to 0, okay? And in chapter 4, I said that you might think this one looks very weird, but at the end, this equation simply means that u and x is independent, okay? And think about what are inside the u. We say that u contains every other information except x, okay, that can affect y, okay? So not everything else in the world affect test scores, okay? So for example, the eye color of a student doesn't affect their test scores, or whether a student have long or short hair, or hair color doesn't affect students' test scores. It is other things, okay, like school budget, school selection criteria, or let's say teacher quality, peer effects, or parents help. All the other things that affect y are included in u. And the reason why we don't include these factors into our regression is because we believe that this assumption holds, which is those things have nothing to do with class size, okay? It is only when class size have nothing to do with all of these, okay, we can say that that means class size is independent of all of these other factors that affect test scores, or we just say that all the other things conditional mean on class size is 0, okay? However, the error u arises because of factors or variables that influence y but are not included in the regression functions. So we call them omitted variable, okay? They are omitted, but they don't necessarily cause bias. And they only cause bias if the conditional mean of them given x is not 0, okay? Okay, so this sentence is the most important thing in this whole page, okay? All of these factors is fine, okay? We don't need to include all of them as long as they satisfy conditional mean equals to 0. However, if their conditional mean given x is not 0, which breaks our assumption then they causes omitted variable bias. Okay, so let's take a look at how we define omitted variable bias. Okay, so the bias in the OLS estimator that occurs as a result of an omitted variable bias, or we call it omitted factor bias. It's occurred only when, okay, let's call these omitted variables Z. Okay, Z can be one variable, can be multiple variables. We just called it Z. So if Z satisfy the following two conditions at the same time, then Z causes omitted variable bias. Okay, so what are these two conditions? First, Z determines Y. Okay, or Z is a part of U. Okay, U is everything that determines Y. And if Z is part of U, that means Z determines Y. And the second condition is Z is correlated with the regressor X. Okay, which means that correlation between Z and X doesn't equal to 0. And so both conditions must hold at the same time for the omission of Z to result in an omitted variable bias. Okay, so we'll have more examples later, and we also have more examples in our quizzes, okay? Don't worry if you cannot understand right now. But first thing you need to know is both of them have to hold at the same time to cause omitted variable bias. Okay, so let's look at this example. In test scores, we believe that English ability is a determinant of your test scores. Okay, if your English is really bad, you can't even understand the question. How are you gonna get a better scores? So English determines test scores. So Z is part of Y. Okay, and then second, is Z independent of class size? And the argument provided here is that immigrant communities tend to be less affluent, okay, and thus have smaller school budgets and higher STR. So in communities that have lower English abilities tend to have higher STR. In that way, okay, then STR and Z is correlated. Okay, so first, Z is a determinant of Y. Second, Z correlated with X. Both holds, so beta 1 hat is biased, okay? Okay, be careful, it's beta 1 hat. The estimator is biased, okay? Not the population coefficient is biased. The estimator, the beta 1 hat is biased. So, in this case, omitted variable bias comes, okay? Here's one more question. What's the direction of the bias? We will talk about that later. Okay, let's just figure out omitted variable bias first. Here's some math. These maths is, I would say they're important, but not necessarily required. Okay, so don't freak out. Here is a formula for omitted variable bias. Okay, beta 1 hat is our estimator. Okay, our estimator is unbiased if all the assumptions holds, but now if omitted variable bias, that means one assumption doesn't hold. So then our estimator is not unbiased. Our estimator minus the population parameter, which is beta 1. Okay, this one we don't know, but we can write it down in our equations. Okay, on top of that is this thing. Is this thing, yeah. And then in the denominator, it is the sample variance of X, where this VI equals to xi minus x bar times ui. Okay, this part you don't really need to remember that. Okay, so how do we look at this one? Okay, so if this thing doesn't equal to 0, then that means our estimator doesn't equal to the that means our estimator doesn't equal to the population mean, right? No, population parameter. Okay, and this thing is for sure not 0, okay, because our estimator is from a sample, but the population parameter is from the population. You never know beta 1, so beta 1 hat is always not exactly beta 1, but we are taking its expectation, okay? So expectation of beta 1 hat minus beta 1, okay? But we want this expectation to be 0, okay? If this expectation is 0, then it is unbiased, okay? Because beta 1 hat has a distribution, but beta 1 is the population parameter that's out there, we don't know. Okay, so this thing will equals to expectation of this giant thing, okay? Left side equals to the right side. So we just drag this down here. Okay, do we know if this is 0? Okay, so the problem comes, okay? Down here, this is for sure not equal to 0, okay? Or this is for sure larger than 1, larger than 0, because a denominator cannot be 0, right? So we only care about whether the expectation of the upper part is 0 or not. Okay, so this part under the least square assumption 1, its expectation will equal to 0 because if you put the assumption of least square assumption 1 into here, the expectation of it, you can get it to 0. Okay, we do not require you to prove it, but that's how we rationalize these mathematics. But if it doesn't equal to 0, then this part's expectation doesn't equal to 0. Okay, all right. So that happens. So that means this thing is biased. Let me change the color. Okay, that means our beta 1 hat is biased. Okay, all right, don't freak out. Just some mathematics, okay? All right. Okay, here is more. Okay, basically it's what we were doing just now. It's just they switched a lot of the notations. At the end, beta 1 hat minus beta 1 equals to sigma u divided by sigma x times rho xu, while rho xu is the correlation coefficient. Okay. All right. So the correlation coefficient, is 0 if the assumption holds. Okay. If the assumption 1 doesn't hold, then the correlation, which is the rho, will not equal to 0. Okay. That is how we triggered omitted variable bias. Okay. All right, so here is the formula. This formula is required, but we'll explain more when we get to the exercise. Okay, let's repeat what we have just learned. An omitted variable bias occurred when z is a determinant of y, or z is contained in u. Second condition, z is correlated with x, which means that rho xu doesn't equal to 0. Okay, and then the OS estimator beta 1 is biased and not consistent. Okay. All right, so let's take a look at this English level example. Okay, First, there is this tabulation of data. Okay, if you compare small class and large class, okay, small class is student teacher ratio smaller than 20, large class is 20 or above. Okay, and if you look at the large sample, small class average is 657, large class is 650. Okay, so large class did 7.4 points poorer. Okay. However, now we want to include English learners. So percentage of English learner means that if you have more English learners, then these people's English is poorer. Okay, so let's look at this part. Okay, so this part, percentage of English learner is smaller than 1.9. We call them good English people or good English school districts. And what's the difference between their small class and large class scores? Small class, 664.5. Large class, okay, 665.4. There is only a 0.9 difference between small class and large class for these good English school districts. And the difference is not significant. Why? Because if your t statistic is 0.3 or minus 0.3, okay, you're not gonna get a significance test, right? You fail to reject that they are different. Okay, so we came to a conclusion that for good English school districts, there's no difference between small class and big class. Okay. Now let's take a look at the bad English school districts. We shouldn't call them bad, but okay. So this one is the school districts with more English learners, okay? Larger than 23% of English learners. And let's take a look at the difference. Small class, 636, okay? Large class, 634. Oh, so they do much poorer than the good English people, right? The good English people get 660s, while the poorer English school districts only get 630s. And what's their difference? The difference is 1.9, okay? So small class did better, but are they significant? They are not significant, right? The t statistic is only 0.68. Fail to reject that they're different. Okay, so after you include the story, and if I ask you again, do you think class size have a causal effect on school scores? You probably would say, I don't think so, right? Because after we separate our school districts into good English and bad English school districts, we just find out that the score difference between small class and large class just vanish, okay, or become statistically insignificant. Okay, so then the previous exercise we did, which is using the whole sample and run a regression of school scores on the class size, is biased. Okay, that beta 1 hat is biased because we omitted percentage of English learner, and we can clearly tell that here English learner did affect test scores, and it does correlate with student teacher ratio. Okay, so here's what we are gonna do. We want to use a regression to do that, and we want to include fraction of English learner into it so that beta 1 can be unbiased. Okay. More precisely is a causal effect. A causal effect is defined to be the effect measured in an idealized controlled experiment. Okay, let's skip this part first. Okay. So the thing is, we did not end up having a randomized class size because we know that districts with better English gets smaller class size, while districts with more English learners gets larger class size. So our assumption doesn't hold. We observe these two conditions that leads to our biasedness of our estimator. Okay. So we have to include it. Okay, I want to skip the control experiment part because it's not really a very good comparison because okay, probably you guys can read this part on your own. Okay. The idea is that using this cross tabulation we just did, we find out that the class size probably has a bias due to omitted variable, which is this English percentage of learner. And we know that percentage of English learner is correlated with the class size. So we end up having a distribution of class size that is not randomly assigned. Okay, think of that as it's assigned, but with a pattern that this pattern, which is related to English learners. Okay, and English learners happen to affect our Y variable, which is test scores. Okay, so we did not have experiment, and our condition is not close to an experiment as well. Okay, that's the basic conclusion that it's gonna reach here. Okay, so how to solve it? Yes, then it comes to our major point, which is this population multiple regression model. Okay, we consider this case of two regressors, x1 and x2. This x1 can be our class size, and x2 will be our omitted variable, which is percent of English learner. Okay, we call all of these x independent variables or regressors. Okay, y is still dependent variable. Okay, so now beta 0 is still intercept. Beta 1, beta 2 will be the slope, but you don't have two slopes on one graph, right? So the graph disappeared. You just think of beta 1 and beta 2 as effect on y of a change on the x, okay? And here's something important. Holding the other variable constant. Okay, so, oops. So beta 1 is the effect of one unit change in x1 on y, holding the other x, which is x2 constant. While beta 2 is effect of one unit change in x2 on y, holding x1 constant. So why do we want to hold things constant? This one is simple if you have any lab experiments, okay? Because for a policy to initiate, you're kind of like hiring more teachers, right? So, but the other thing doesn't change. You don't change the students into more English learners or less English learners. So you want causal effect, then you have to hold all the other things constant. Okay, so multiple regression enables you to do that. Okay, it enables you to hold other things constant while just change one unit of the thing you want to change. In this case, its student-teacher ratio. Again, U is the error, okay, or all the other factors that affect Y and not included in X1 and X2. Okay. So consider the let's take a look at how the maths can be written. What does the math tell by holding all the other things constant? Okay, so consider that you have two population line or population regression line, okay? This line you cannot really be visualized, but you can still call it a line, okay? It cannot be visualized, so you cannot really goes Y and then X, right? Unless you can write a 3D. Okay, this is difficult. Okay, so it's very hard to visualize. What's this line gonna look like? But think of a multi-dimension space, okay? Be abstract, be a little bit imaginative. Okay, there's a line there. And this line is 3 dimensions, okay? There's an X1 and X2. And you can add more X variables if you want to, okay? If there are other X variables that causes the omitted variable bias, then sure, include them, okay? Now, if I change X1 by delta X1, okay, but I don't change X2, so X2 is hold a constant, okay, X2 is still here, it's still constant, then I will have delta Y unit change in Y, okay. This so X1 changed by delta X1, Y changed by delta Y. Okay, so we want to take this out of the question, of the equation. It's gonna look like this. So before is the original regression line, after is this, and if you subtract before and after, okay, and the right-hand side, you have delta Y left. In the right-hand side, you have beta 1 times delta X1 left, okay? Because beta 0 is canceled. Beta 2 X2 and beta 2 X2 are canceled. Beta 1 times X1 and beta 1 times X1 is canceled. So what you have left is beta 1 times, okay, don't forget that, beta 1 times delta X1. Okay, so look at this difference. Okay, so this difference is what we're looking at. So this difference, if you put X1 to this side, right, then you get this equation. Okay, too messy. Look at this question. Look at this equation. If you put X1, delta X1 to the left-hand side, then you get this equation. Okay, so beta 1 is interpreted as delta Y divided by delta X1 holding X2 constant. While beta 2, it's the same way of the equation calculation. So you get beta 2 equals to delta Y divided by delta X2 holding X1 constant. Okay, so holding the other independent variables constant is very important when you interpret beta 1 and beta 2. How about beta 0? Beta 0 is predictive value of Y when X1 and X2 both equal to 0. Okay, so does that make sense? Depends on the question, right? If X1 and X2 both equal to 0 makes sense in reality, then beta 0 has a meaning, okay? All right. Okay, so these mathematics are very simple, so you guys are required to know it. Okay. All right. Okay, so with two regressors, the OLS estimator solves this problem. Okay, still remember what is OLS? Ordinary least squares. Okay, it means that you have to least a square, which is minimize the summation of this part. Okay, so if you solve this optimization problem, you will get beta 0, beta 1, and also beta 2. This use Odin's estimator of beta 0 and beta 1. Oh, estimator of beta. Okay, so this gets you beta 1 hat, beta 2 hat, and beta 0 hat. Okay. All right. Okay, let's take a look at an example. The first regression is what we have run before. Test score is 698.9 minus 2.28 times STR. Now, if we include percent English learners, then we get beta 0, which becomes 686. Okay, but beta 0 doesn't make sense because STR cannot be 0, right? Okay, and we have beta 1, which is minus 1.1, and beta 2, which is minus 0.65. All right, so clearly what happened to beta 1? Beta 1 changed, okay? Beta 1 changed by at least half, okay? Before it's minus 2.2, now it's minus 1.1, okay? Why is that? Because this one is biased, okay? All right. Page 22 is multiple regression in STATA. In the following chapter, we're going to learn how to run regressions in Excel. So we can skip this part first. Oh, probably let you take a look at the Probably I'll let you take a look at the t statistics. Okay, see, so the t statistics are all pretty large, and the p-value are more pretty small. So we can reject, right? We can reject null hypothesis of beta 1, beta 2, and beta 0. That we reject that if they are equal to 0. Wait, okay, the null hypothesis is that they are 0, and we can reject the null hypothesis that they are 0. Okay, more on this printout later. All right. I want to talk a little bit about SER and oh no, too fast. Measures of fit. Okay. So pretty much done with multiple regression. It's introduction part. Now let's move on to measures of fit. So R square is still one of our most important thing. This is what you always need to know, which is fraction of variance of y explained by x. Okay, so here, what is x? X means all the x in your equation. Okay, it can be x1, x2. If you only have x1 and x2, if you have, let's say, 10 independent variables, then R squared is fraction of variance of y explained by all of these independent variables, okay? So what is new? This one is not new. Actual equals to predicted plus residual. This one is not new. R squared is not new. Adjusted R squared is new. Okay. SCR and RMSE are not new, but not really required because we rarely use it. Okay. The only thing you need to know is just SCR has the same unit with y. All right. So adjusted R square is new. Okay, we'll talk more about it later. Okay, after we pass this SCR and RNFC. Okay. All right. Sorry, let me rephrase this again. The first line, actual equals to predicted plus residual. So actual is y, predicted value is y hat, which is the point on the line. Okay, residual is u hat. Okay, all of these are not new. And SCR and RMSC are not new, but not really required. R square is not new. Okay, but adjusted R square is new and is required. Okay. All right, so let's take a look at what the hell is adjusted R square. Okay, R square is a fraction of variance explained by all of the x. When we only have one single regressor, R square equals to ESS divided by TSS, which equals to 1 minus SSR divided by TSS. The name of these is not really hard to remember. It can remember ESS explained, okay? Explained, okay? T is total, R is residual, okay? So there are three different parts, okay? TSS equals to ESS plus SSR, okay? I think I've mentioned this before, I'm not sure. So total SS equals to explained part plus the residual part, which is not explained part, right? So R square will always increase when you added another regressor. Why? Because you're always introducing something else that can explain the unexplained part. Okay, think of this. Think of class size. So at the beginning, it's just class size explains test scores. But then you think, oh, maybe students' IQ matters. So then the students' IQ come in and it will explain some of the other variations that is not explained by the class size, right? And then you add some more things, like let's say teachers' patience or teachers' quality. Okay, so teachers' quality will explain some more of the parts that is not explained. Okay, so the more information you introduce, as long as they make sense, as long as they are somehow related to why, or somehow that determines why, or as long as they're not exactly zero effect, then they will always increase R square as you add more information, because you can explain more about your dependent variables. Okay, intuitively, it is more information is introduced, then R square will for sure increase, unless the new information's effect is exactly zero. Okay. So there's a bit of problem with that, because what if you just keep on adding variables to make R squared too much? What's that? Why we don't want it? R squared. Okay, let me do it this way. Why we don't want to keep putting in new x variables to increase R squared, on and on and on. Okay. Okay, if you continue to learn machine learning, you will learn something called overfitting. problem of overfitting. Okay, so mathematically you can prove it, but intuitively it's just very simple. That is, you pick explained noise that you are not supposed to explain. Okay. Okay, sounds a little bit trivial. So problem of overfitting, if you learn machine learning, you come across this word called overfitting. So the problem of that is, if you keep adding S variables on and on and on, then you probably will end up having a better and better R square. Okay, you can continue doing that for the rest of your life, kind of like just adding more things into your regressions. But why do we not do it? Because overfitting, because the new information you introduce might mistakenly picked up some noise. Okay, what if this noise is not, and you're not supposed to explain noise, because noise is so trivial. Noise always exists, and noise are, how do I say? Noise is something that occurred randomly, and you're not supposed to explain them with some things like income or IQ or teacher quality, all of those things. You're not supposed to explain those things. You need to leave some room for noise, because if you picked up too much noise, then you cannot explain other things. You cannot make predictions anymore, because how do I say? When you make predictions, you cannot predict noise. Okay. We can talk more about that if you guys are interested. Okay. But this is a problem. Okay, R square is problematic. We need something else. So to overcome that, we have something called adjusted R square. So what does it do? Adjusted R square corrects the problem by penalizing you for including too many regressors. Okay. It doesn't necessarily, so adjusted R square does not necessarily increase when you add another regressor. Okay, this part is required. If you add another new information, as long as it's not exactly 0, then R square will always increase. But adjusted R square will not always increase, because it penalizes you for adding another regressor. Okay, so what's the equation for adjusted R square? This one is required. You guys should take it down. And adjusted R square is smaller than R square. This one is also required. Okay. One thing to mention. What is K? K is number of X in your regression. Okay, so for example, if you only have X1, X2, then K is 2. If you have X1, X2, X3, then K is 3. Okay. And you guys should know lowercase n by now. It is sample size. Okay. All right. Okay, how about this part? How about this part? SSR divided by TSS. This is actually 1 minus R square. Okay. Because SSR is the part that your model does not explain, right? So this part is 1 minus I square. Okay, unless you don't know. All right. Oh, square, UARE. All right. And R square, adjusted R square is always smaller than R square. This one will also show up in your multiple choice. Okay. All right. Let's take a look at this example. If you only have two variables, your R square is 5%. Your adjusted R square doesn't show up because you only have one variable. However, if you have two variables, then R square increases because you add a lot of more information into the equation. But this thing is always smaller than R square, okay? So what precisely does this tell you about the fit of the regression comparing to 1? We know that 0.426 is larger than 0.05. So the second equation definitely has more explained power than the first equation. And how about adjusted R square and R square? So adjusted R square is not that much smaller than R square in the second case. Okay, the difference is only 0.002. So we would say, okay, the penalty is not that big. Okay, then we should say that, okay, it's worth it to include the percentage of English learner because we gain a lot of explanation power and the penalty is not that big. Okay. All right. Okay. Okay, so that's everything about measures of fit. Let's take a look at the assumptions. Least square assumptions for multiple regression. So here is a multiple regression, okay? You can have k amount of x variables. You can have x1, x2, all the way to xk. And what is not new? Conditional mean is equals to 0 is not new, okay? Which says the conditional distribution of u given x has mean 0. This also means that all the x should be not related or correlated to z or to u, okay? Better say u, okay, to the error. All of the x, all of these kx should not be correlated with anything inside a u. If anything inside a u is correlated with x and that thing also affects y, then you have omitted variable bias. You have to try to observe it and put in your equation. The second thing is also not new. Your sample should be random, okay, or it should be IID. The third thing is also not new, okay? All the x variables and y have finite fourth moment or have rare outliers. So the only thing new here is there is no perfect multicollinearity. All right, so we'll take a look at the fourth one, okay? Let's skip this one. And the second one and the third one is very easy to understand. Okay, so what does perfect collinearity means? Okay, so for example, if you regress, oops, this looks ugly. So example 1, if you regress y on x1, x1, which means that you accidentally run you regress y on x1, x1, then this is multicollinearity because you cannot have two identical independent variables. Okay. So if you put this in STATA, STATA is going to drop it for you because STATA thinks that you don't need to add the same information. Okay, because two exactly same information is useless. Okay, so this is the first example about multicollinearity. Okay, so this is the first example, and let's take a look at the next example. We have better idea about it. Oh, there isn't other examples. Okay, let me probably use a new slide. Okay, so the first example is regress x1 on regress y on x1, x1. Examples of multicollinearity. Okay. Or perfect multicollinearity. Okay. Example 2. Regress y on female and male. All right. So what's wrong with this one? Problem of this one is that female equals to 1 if it's female. If it's 0, it's male. Okay. While male equals to 0 if it's female and 1 if it's male. Okay. So did you add extra information by including male? You don't. Okay. Because by looking at female, I already know whether this person is a guy or a woman, right? Because if female equals to 1, then I know it's a woman. If it's 0, then I know it's a man. I don't need an extra variable to tell me about this person's gender. Okay, suppose we don't have other genders. Okay, suppose we only have 2 genders. Well, you can have other genders, but in this case, we only have 2 genders. So I don't need an extra variable to tell me there is this person's gender information. Like the next one doesn't add any new information into this model because it's the same information, just like example 1, that x1 already tells me everything about x1. If you put on x1 again, it's not adding any new information into it. Then it's multicollinearity. Okay. Or let me put it this way. You're adding the same information into the model. Okay. Adding completely same information into the model. Okay, so how about this one? Regress y on x. X is weight in pounds. X1 is weight in pounds. And then X2 is weight in kg. Okay, what's wrong with X1 and X2? So X1 and X2 are still exactly same information, right? Okay. So I don't need x2 to tell me x1's information, because by looking at x1, I already know this person's weight in pounds, and by calculation, I can tell this person's weight in kg. Okay, so they all have linearity problems, and if you want to write it down in mathematics, it looks like this. Okay, and the first one, x1 equals to x1. In the second one, x1 equals to 1 minus x2. Okay, because when x1 is 1, x2 is 0. When x1 is 0, x2 is 1. So x1 is 1 minus x2. And 3, how about 3? x1 is x2 times a coefficient, let's say k. Okay, let's say kg to pounds conversion. How much is that? 2.2 or something, right? Okay, so all of these threes are perfect linear functions. Okay, all of these threes are perfect linear functions. And if this exists, then we call it perfect multicollinearity. Okay, if perfect multicollinearity exists, then the fourth assumption is wrong. Okay, so let's clear this part. Let's look at the formal definition. We'll return this shortly. Oh, here, okay. Perfect multicollinearity is when one of the regressors is an exact linear function of the other regressors. Okay, so some more example is this. The first one is you include STR twice. The second one is you regress test score on D and B. While D is small class and B is another dummy that is large class. Okay, and D and B is exactly opposite. So it's the female male example, and there is a perfect collinearity here. Okay, so let's go into the dummy variable trap. Okay, so dummy variable trap is a good example of perfect multicollinearity. If there is two categories, usually female and male, you only need one of them. Okay, you only need to put one of them into the equation. So solution to dummy variable trap is if you put two of them in, then you fall into dummy variable trap. Okay, what's the solution? Just throw one of them out. You can throw female out, you can throw male out. I just need one of them to know what's the gender of this person. Okay. Another example is to omit the intercept. Okay, so this one is not really recommended, but you should know that this is another example. Not recommended, but useful. Okay. I don't really imagine what kind of situations it's very useful, but it is one of the solutions. Usually we just throw one of them out. Okay. So perfect multicollinearity usually represents a mistake in the definition of the regressors. If you have perfect multicollinearity, your statistical software usually can identify it and help you drop one of them out. Okay, the solution to perfect multicollinearity is simply to adjust your list of regressors so that they no longer have this perfect multicollinearity, or they no longer have any linear function towards each other. Okay. I think I have more information to add here, but let's talk about it when we're doing exercises. Okay. But I think dummy variable trap is very common. And at the beginning, you think it completely makes sense. Female and male, you put two variables in, and then you realize I just need one of them to know the information, because the other one is a linear function of the other one. Okay. All right. We also have imperfect multicollinearity. So imperfect multicollinearity is not one of the four assumptions, but it can also occur when two or more regressors are highly correlated. Okay. So in terms of highly correlated, what kind of things can be highly correlated? Okay. I think two things can be, do you guys know SP500? So it's a very typical market index, right? So every day, SP500 is one of the market index to tell us whether stock market is doing good or bad today. It's gonna be highly correlated with other indexes. I think there's the Dow and there's other indexes. Okay, there are so many indexes, but they will be highly correlated every day because all of them are a combination of a lot of stocks on the market. So if you put these two into the X variables, okay, I don't know what your Y variables can be, but you will end up having imperfect multicollinearity. Okay. They don't violate the fourth assumptions because they are not exactly linear relationship with each other. But you will end up having imperfect multicollinearity. So what's the problem with this one then? It means that your regression coefficient probably will be imprecisely estimated. Okay. Because even though they are not exactly the same information, they are almost the same information. Okay. Think of different market indexes in terms of how they tells you information about how the market is doing. They are very, very similar. So the problem is not you can't run this regression. It's just your beta probably is imprecise. Okay. The math CSW appendix 6.2. This one is not required. Okay, you just need to know definition of imperfect multicollinearity. Okay. The last part of it is about control variables and conditional mean independence. This part is honestly not required. So if you guys are interested, you can read page 40 and after. Okay, I'm not gonna cover it here. Basically, these are just some more information about how we chose as control variables. Okay. There is this information here that says you can have percentage of English learner, and you can also have lunch percentage, which is percentage of people who receive free lunch. Okay. So it's probably a causal variable and control variable because you want to control people's family income. Okay. And why do you want to control family income? Because you can argue that family income is first affecting test scores. Second, family income might be related to STR. Okay, so including that into it, you will end up getting a different beta 1 for STR again, right? And then I think These are just some mathematics. These are definitely not required. Okay. So that's it. We'll talk more about these things when we talk about hypothesis testing in chapter 7.